Piping vibration, quantitative mainline LOF assessment for pipework, analyzing pipeline integrity through detailed data evaluation. This assessment based on guidelines for the avoidance of vibration-induced fatigue failure in process pipework by Energy Institute. Purpose and scope of T2 quantitative mainline LOF assessment for pipework. The T2 module focuses on converting qualitative assessments into quantitative likelihood of failure, LOF, values for pipework subject to vibration-related fatigue. Its purpose is to provide a structured method for calculating LOF for each excitation mechanism identified during qualitative screening, T1. This quantitative approach helps prioritize risk mitigation and corrective actions. The scope includes main process lines containing flowing fluids, and the extent of assessment varies depending on the excitation mechanism. The module applies to both new designs and existing plants, ensuring that engineers can make informed decisions based on actual operating conditions. When plant-specific data is unavailable, sample input parameters from Appendix B can be used, but actual measured values should replace these whenever possible. The methodology emphasizes accuracy and consistency, requiring engineers to consider geometry, fluid properties, and operational conditions. Ultimately, T2 ensures that high-risk areas are identified and addressed before failures occur, reducing downtime and improving plant safety and reliability. Mechanisms covered in T2. T2 addresses 8 primary excitation mechanisms that can lead to vibration-induced fatigue in pipework. These include, number 1, flow-induced turbulence, which occurs due to turbulent energy in fluid flow. Number 2, mechanical excitation from machinery such as pumps and compressors. Number 3, pulsation from reciprocating or positive displacement pumps and compressors. Number 4, pulsation caused by rotating stall and centrifugal compressors. Number 5, flow-induced pulsation at deadleg branches. Number 6, high-frequency acoustic excitation from pressure-reducing devices like control valves. Number 7, surge and momentum changes due to fast valve operations. And number 8, cavitation and flashing at discrete pressure drops. Each mechanism has unique characteristics, input requirements, and calculation methods for LOF. Understanding these mechanisms is critical because they influence different parts of the piping system and require tailored mitigation strategies. The module provides detailed flowcharts and formulas for each mechanism, ensuring engineers can systematically evaluate and quantify risks across the plant. Inputs and calculation method. Flow-induced turbulence is a common source of vibration in piping systems. The assessment begins by gathering key inputs: external pipe diameter, D_xt, wall thickness, T, maximum span length between supports, L_span, and support type classification, stiff, medium, or flexible. Fluid properties such as velocity, V, density, ρ, and gas dynamic viscosity, μ_gas, are also required. For flexible systems, structural natural frequency, F_n, may be considered in advanced screening. The calculation involves determining V⁻² based on actual flow conditions, computing the fluid viscosity factor, FVF, and classifying support arrangement to estimate fundamental natural frequency. The flow-induced vibration factor, F_V, is then derived from tables or formulas based on pipe geometry and support type. The LOF is calculated using LOF equals FVF times F_V times V⁻². For flexible lines with F_n between 1 to 3 Hz, an advanced screening method refines F_V and LOF to avoid overly conservative or non-conservative results. This ensures accurate risk prediction for systems sensitive to turbulence. Mechanical excitation and pulsation risks. Mechanical excitation occurs when piping is connected to or near machinery, such as pumps, compressors, or engines. LOF values are assigned based on equipment type: reciprocating compressors or pumps, 0.9, diesel or gas engines, 0.8, screw machines, 0.6, centrifugal pumps, 0.4, and electric motors, 0.2 to 0.4 depending on size. If detailed dynamic analysis confirms no frequency coincidence, LOF can be reduced to 0.4. Pulsation risks from reciprocating or positive displacement machines affect piping up to the first major vessel. If power is below 112 kilowatts and discharge pressure under 35 bar, or if API 618 and or 674 analysis has been implemented, LOF is 0.4, otherwise, LOF is 1. 0. Rotating stall pulsation in centrifugal compressors is assessed similarly. Near stall operation yields LOF of 1.0, while absence of stall characteristics reduces LOF to 0.2. These mechanisms require careful evaluation because they can generate high cyclic stresses, leading to fatigue failures if not mitigated through design or operational controls. Flow-induced pulsation, acoustic excitation, surge, and cavitation. Flow-induced pulsation at deadleg branches can cause resonance and vibration. Each side branch is assessed individually, and the highest LOF governs the main line. Screening considers Reynolds number, branch-to-main diameter ratio, and frequency ratios. High-frequency acoustic excitation arises from pressure-reducing devices like control valves and orifices, affecting welded discontinuities. Sound power levels, PWL, are calculated and propagated along the line. If PWL exceeds 155 dB, fatigue life multipliers are applied to compute LOF. Surge and momentum changes occur during fast valve operations, especially in liquid or multiphase systems. Rapid closure can generate high surge pressures, requiring LOF calculation and possibly detailed surge analysis if upstream lengths exceed 100 m or pressures approach design limits. Cavitation and flashing are localized but severe phenomena at discrete pressure drops. Flashing typically results in LOF of 1.0, while cavitation yields LOF of 0.7. These mechanisms demand targeted mitigation, such as installing pulsation dampeners, low-noise trims, or adjusting valve timing to reduce dynamic loads. Best practices and LOF rollup. Accurate LOF assessment depends on reliable input data and proper application of formulas. Engineers should use actual operating conditions for density, flow, and sound speed rather than standard reference values. For flexible piping systems, measuring natural frequency is essential for advanced screening. Valve noise data should be validated with manufacturer specifications, and surge analysis should be performed when upstream lengths exceed 100 m or pressure surges approach design ratings. After calculating LOF for all applicable mechanisms, the governing LOF determines prioritization for mitigation. Common corrective actions include upgrading supports, installing pulsation bottles, using low-noise valve trims, rerouting dead legs, implementing surge control systems, and adjusting anti-stall controls. This integrated approach ensures that high-risk areas are addressed effectively, reducing the likelihood of vibration-induced fatigue failures and improving overall plant reliability.